Welcome everyone to my talk about 3 technical solutions in Mortal Kombat Mobile. My name is Juan Gomez. I joined Sperasoft in 2016. Since then, I work in projects like Injustice Gods Among Us and WWE Mortals. In 2020, I was the lead developer in Mortal Kombat Mobile. And since then, I actually moved to other projects and a technical director. A bit of our company. So we are a co-dev studio that has right now 11 offices in 8 different countries and almost 1,000 people. Here are some of the clients we work for. Regarding Mortal Kombat Mobile, so also known as MKM, so it's a game that was released in 2015 for iOS and Android, and Sperasoft participated in the development of it. The game was quite popular and even to this day is still receiving regular updates. In terms of technology, it was originally developed in Unreal Engine 3 and since then imported to Unreal Engine 4. In particular, 4.19 is the version that we had the longest. But before we start, let's get to know a little bit about each other. So, how many of you, actually, if you could raise your hand, know about Mortal Kombat? I guess, yeah, a lot. What about, in particular, Mortal Kombat Mobile? All right, some. Okay. How many of you programmers? Okay, most of you. And what about Unreal Engine? People working on Unreal Engine? All right, awesome. Yeah, thanks. So yeah, I hope that this overlap will be good and you will get something interesting from it. So basically, we will be talking about 3 different things. So we have different challenges in different areas that we want to start a little bit about. And for each of them, we are going to show you the problem that we have, what is the initial state that we were like with the data, right? What tools we used to gather this data and to come up with the solutions, and solutions that we came up, and the final state. So basically, there won't be like super advanced topics here, but obviously you need to know the basics to follow. Also, the purpose of this talk is not just to tell you, okay, so we did this. It's also for us to tell you like why we did it, how we did it, which tools we used. So hopefully this can help you and you can take the experience to your projects. All right, so let's talk about the first point, which is UI optimization. So basically, mobile games, they are quite, they have a lot of user interface, a lot of menus, animations, they're heavy. We have a lot of devices that are low end. For example, we were supporting iPhone 6 and Android 5 devices, which are considerably slower than what we have nowadays. So if we take a look at the first example here, this is the collection menu. So we have around 20 cards on the screen. Each of those cards contains like a lot of children, like 50 widgets each. And so there is a lot of we can see here a video where we have the profiler. I don't trust you will be able to see those numbers, but I will show the data later. Basically, we're lowering. We can see here the performance, right? So we were there's the beginning of the optimization. We are talking about around 20 FPS. So we have two numbers we care about. So one is the idle tick and another is the scrolling tick. So the idle tick is when nothing is moving on the screen, and that's okay, but I mean the player doesn't care about it. The player cares about the responsiveness while they are interacting with the menu. So we need to improve it, and so we begin. So the first thing we want to do is talk a little bit about the tools we have. So basically, if you want to debug or like profile UI in Unreal, you want to use stat slate. So it will show you interesting things like what's the total tick time, what's the rendering tick time, what is the amount of widgets you have on the screen, how many draw calls you're doing, and so on. This in combination with unit graph, which is kind of the same as stat FPS, right? It tells you what your bottleneck is. So you can see here the blue line. So the blue line is the rendering tick, and you have the red line, and the red line is the game tick. So if the red line is above the blue line, that means we are CPU bound, and otherwise we are GPU bound. So what we know by just looking at it quickly is like our problem is CPU. Mostly it always is for UI. So the first thing you want to do when you want to tackle like how we can improve the performance in this menu is probably looking at what already tools exist, right? So we at this time recently Unreal introduced invalidation box. So in case you don't know what this basically it takes all the widgets that are on the particular element in the UI and transform it into a texture which will be later cached. So I mean everything needs to be translated into a texture eventually, but this is saving it for future frames. So if nothing is changing here, we already have everything prepared. So using it is pretty simple. So basically you just put it in the hierarchy. As long as it's enabled, can cache, it will cache everything which is under it. For example, we have this element under the invalidation box. You can mark it as is volatile, so the invalidation box will actually ignore it in case you have something that is going to change every frame, but you don't want to move it outside of the hierarchy to a different place. You can keep it there if you turn it on. I can tell a bit more about some other optimizations that are going on here already in this place. So basically at the very bottom, you can see something called energy bar slot. So that's another thing we're doing. Basically, we try to reduce as much as we can from the card and from some other widgets, and only add it on runtime if we need it, right? Which helps with a lot of things. Yeah, the energy bar in particular, it's a big. It was giving us a lot of performance issues. So I will explain it later. So why we want to use invalidation box? We can talk a little bit about how Unreal processes the frame. So basically we have like a game thread, and the game thread is going to do the regular update on the world, like things like physics, things like a game logic, right? And then we have the UI part of the tick. And the UI is doing two things. So it's called the pre-pass and it's doing the on-paint. And I will explain later what this means actually. But for us, in terms of invalidation box, what this means is like we don't, we will save all these calculations. Next frame, we will need to do them again. And of course, later this information is going to be used in the render thread. We run in the stream, but we also need to draw the slate. And yeah, the texture from the invalidation box will be used in this process. Okay, so here we have a video of how it looks after the. Thank you. We see some performance improvement. The numbers probably you can't see, but maybe later when there will be a video, it will be a bit crispier. But again, the data is here, so we have a considerable improvement in our benchmark, and we are right now on 30 FPS. So I recommend to use this feature if you didn't know. I'm sure in Unreal Engine 5 it's much more stable and definitely helpful. So after we use like what the engine provides, we need to start looking into how we can improve our code. So I'm talking here in particular about about Visual Studio. And the Visual Studio is quite simple to use for profiling if you've never used it. So basically, when you are debugging, you need to enable it by pressing this button. Once it's enabled, you can start recording. And once you pause the profiling, you can inspect the results of what you analyzed. So it looks like this. You have on the top the kind of call stack with time, how much we're taking for a particular function, and here in the code you can navigate it. It's very helpful and convenient, and it's kind of reason why I'm talking about it, because Unreal has really good tools, right? Unreal Insights and so on that you can use, but Visual Studio for a programmer it's just in some cases more convenient, and also you can actually take the experience and use this in other game engines. So in terms of what we want to optimize in the code, usually you want to always start with like regular culprits. So that's like the init method and the tick method, things that they are run often, and you can really polish and make very fast. So here we have a particular problem that we found. It has to do with something kind of silly, because we were trying to access some information on init from the player profile, but we were saving the player profile afterwards, even though we were not changing anything. So that's something we identified with this. Obviously, changing it is not a problem at all. So it was super important for us from another optimization that existed. So in that menu, we use recycling scrolling list. If you never heard about it, basically it's you have a list of elements, and instead of having creation and destruction runtime, or having like like all of them loaded at once, you have the virtual pool that it's all the time recycling elements. So one element goes out of the screen from one side, so it's going to the other side, is being recycled with the new data and so on. So that means we are initializing our elements all the time as we scroll, right? And if you want to know a bit in a nutshell how this code will look like for the scrolling list, so basically whenever the user scrolls, we calculate what's our new like first line or like point of reference. We calculate how much we have moved. It's possible that we move more than like one line per frame if like we have very low FPS, and so we just remove it from one side, add it to the other, and initialize the data. So the fix for this, as you can see, makes that this call over here is not even appearing as in the profiler. So it means like it's fast, very fast now. And in the terms of the result, so we can play the video, please. So we can see that we are reducing the spikes a little bit. All right. So the data that we have here shows some improvement, but actually it's not a big improvement because this benchmark is like on PC. I did for this presentation with SSD and so on, and it was a problem, a bigger problem on devices where you have to access like internal memory or like external memory, and it was a bottleneck there. But everything counts. So the next thing, as I mentioned before, the tick method. So we want to initialize the tick. We want to optimize the tick method. You just need to go there and find it. Okay, so here we have this call. Here we have this call, right? So how can we optimize it? Like for example, we have a get energy method, which has to do with the energy bar I mentioned, right? So basically, we are in order to calculate the energy of the particular card, we do it. It's for some reason time consuming, but it doesn't need to be because we don't even update this so often. The energy is regenerating like super slowly. It takes like, I don't know, 10 minutes. So it was even being calculated for cases where the energy was already full. So there wasn't really nothing to update or calculate there. So yeah, this may be anecdotic, but I hope you can like apply to your particular projects. Once you fix it, so it went down to 0.14, I think 0.24 synchronized properties method. And here we have another video of like result of this. So actually now what you want to do next, because you may have noticed we optimize our code. It wasn't really terribly unoptimized, right? And we gain quite some profit, but we still not even close to our goals. Let's say 50 FPS, or sorry, 60 FPS. And there are more things I'm not going to mention. Like for example, we optimize localization. So usually when you get in like a localized string, it's kind of slow. So if you can cache it, it saves a lot of time. You can move a blueprint code to C++. This is another thing we did, so we don't have more blueprint code in this particular menu. In some cases, like 10 times faster. We also rework widgets, so the less widgets you have, the better. We had some, like, let's say, reduced using masks or like tricks. You can like go, let's say, something that was previously 10 widgets separated because the artist just made it like this. You can trim it to the, say, one widget only. But anyway, how can we continue from here? We actually have a tick from the slate itself, right? It's very time consuming, and it's much more time consuming than anything we optimized so far, because we're just optimizing the small things in our code. And you can actually go and profile the engine, see what is going on. Maybe there is a problem in the engine, or maybe there is not. Maybe you are using things in some wrong way, or you can figure out better ways how to use your the engine to do things faster. So we start going deeper, right? So we have a tick here, and we see, okay, we are drawing and doing the pre-pass. So that's the things I mentioned before. So it's taking quite a lot of time. If we go deeper, we see that we are calculating layout size for text, which is taking a lot of time, and surprisingly, it has to do with the cache. So we have a text layout cache, and we are calculating text size for it. Even though nothing changed, and it's supposed to be a cache. So what's going on? If we look at the profiler here, we can see that it's showing that we are doing 384 text layout calls per frame when nothing is moving, even though we don't have so many text in the game, on the screen at this moment. So something is definitely going wrong, and we investigated what was the issue and actually found out that it has to do with scale boxes. So basically, this is kind of a real issue where you have a text, and this text is under scale box. In this case, so the text doesn't go out of the card. And there is another scale box up in the hierarchy, right? They both will mess up with the cache of the texts. So, yeah, to go a bit in depth with this, basically, when we start with the tick, we're doing first the pre-pass. And the pre-pass, basically, it's going through all the elements in the UI, in the hierarchy. It goes from the child to the parent, and later we will paint them. We paint them from parent to child, okay? But when we're doing this iteration and we're going through the children up in the hierarchy, right? We do the text and we cast the size or any other things we need. Later, there is a scale box, okay? But the scale box is affecting all the children. So now we need to do another pre-pass and like recalculate everything. And that's okay when there is only one, but if we have another scale box in the hierarchy, now we are going to override the cache. So the cache is being overridden per frame multiple times, and it's unique, so it basically becomes useless. Our fix for this was a small, not very intrusive engine fix. So basically, instead of having like a unique cache for this, we have like a map. So basically, when we do the calculations for the text, we store them in the cache, and then, next time we come here, if we already have it calculated, so we don't calculate it again, right? Excuse me. If anything changes in the text, we just clean the cache in a conservative way. Here is how it looks. So it went down from 43 to 28%. Of the computational time, the draw children here from 28 to 18 and from 11 to 6. The compute desired size went from 5.9 to 1.1. And in general, we have like and you can maybe even notice here at the bottom, this is the unit graph. It doesn't have spikes that you used to have. So in terms of performance, a big gain. We almost reached 60 FPS this time, so that's great. However, we already did used the recommended features of the engine. We already optimized our code, and we even optimized engine code. And we want to go further. So we know we're not actually bound by CPU anymore. And I already talked for quite a lot of time, so maybe someone can help me and tell me if it's not CPU or GPU, what can be our bottleneck now? Memory access, yes, right. So we are loading the access. We are loading the images, and we are doing it synchronously, right? So we use the try load method, which it's good. You know, it has cache. You don't load things multiple times. It's convenient, but it blocks the main thread. So we started using a synchronous method called load asset list. It basically more work. You need to have a placeholder for the image. You need to have a callback for like when the image is loaded to replace it, but it doesn't block the main thread, and this is the key. So we have actually here a couple of old videos. These are real videos from device, not like the previous one I saw. So this is before without asynchronous loading. So if you could play the video, please. So you can see the terrible frame rate there, the spikes. It's only the first time you go through the collection, right? Once the cards are loaded, it's okay. So now we have the example, another video with asynchronous loading turned on, right? So as you can see, this is kind of like a stream case because the cards are taking a long time to load, but you know, the scrolling is super smooth. And we have here the last video where we saw in our benchmark the final result with all the optimizations in place. Thank you. So I hope you can see the difference already, even though with this projector. In PC, the images load anyway instantly. Just at the end, you can barely see the placeholders. So this is how it looks right now. So we made it to 60 FPS, and just as a quick note to point out that we started with basically 14 FPS as an idle tick, 14 milliseconds, and now we have 14 milliseconds for the scrolling tick. So this just shows how much of the processing was being wasted. So we continue to the next part. So that was the longest, and I did it much quicker than I was expecting. So I hope we will have some time for questions. We go to the next part. It's a bit connected, but you know, random crashes, not really on a type of optimization, but rather let's say optimization of our crash rate, right? So our crash rate was around, like our crash-free rate was around 95%. So that means that we having like 5% sessions which may end up in a crash. So we want to reduce it by half at least, and so we start analyzing what type of crashes we have in production. So basically, some were crash on close actually. So a mobile phone player will not even notice this because they just close in the game and the game crashes. Okay. Others are related to low-end devices. So for example, we have you know, lack of memory. This will be in the last part of the presentation. And then the other part about bugs that cannot be reproduced by QA until it's too late, right? So what does it mean? Like you can say it's not deterministic, but basically what this means is like it cannot be reproduced yet because, you know, I mean, the computer is pretty deterministic. So let's see what could be the difference, right? So we start to reproducing, you know, using the same, you know, reproduction steps as the players. but we still cannot reproduce it. We train with the same build version, but we still cannot reproduce it. Same environment, server, okay, the same device, stack model, the same operational system, the same player save, everything is the same. Is the same weather, okay? What can it be? What is the difference? Does anyone have an idea? What could cause this? Other applications on the phone. Yes, it's a good hint. Other applications in the phone per se will not usually interact or affect your program, but they're consuming the same memory, right? Yeah, there are some such cases, but we're not going to discuss them here. So basically, it has to do with the garbage collector. So basically, the garbage collector is called randomly, and you can call it manually if you want using this function. But generally, it may be called more often if a lot of applications are running on the phone. So how the garbage collector works in a nutshell. We have a set of U objects in Unreal, right? And we delete one of them. Then the garbage collector comes and it checks every object in the game, and it sees if you can find the reference to the root set for this object. If you cannot, like in the case of these childs of this object, they are garbage collected, okay? And this one object is not going to be garbage collected because you can find a different connection to the root set from here. And that's because of this reference that we have here. But a very important thing to understand about the garbage collector in Unreal is that this is only going to work if this reference here is a U property. If this is not a U property, you can say this object bye-bye because the garbage collector is going to take it. And later you're going to try to access it and random things going to be there. So these are the things we were fixing. In order to fix them, fixing them is trivial, right? The problem is actually finding them. So for this, you want to use something like Firebase or Crashlytics or some tool that will collect data from live, from your players. What are they doing when their game crashed? How many times are crashing? What new crashes per version? Everything, right? And most importantly, the call stack. So if we have a call stack, we can try to fix it, right? So for example, here is an example of one bug, right? There is a call to some function that ends in the crash, right? Apply talents in this case. Okay, let's go to the code. So here is the line. So we know that in order for the game to crash, something is null or it has been garbage collected, right? So you start looking at what can be. So there are some table here that we accessing. Maybe this is it. Maybe this talent item server data is. You just need to go each one by one, analyzing could that be null or garbage collected. So in our case, it has to do with this variable over here. So basically, we are accessing the talents from the player character definition, and those were not marked as U properties. Simple fix. You just need to make sure, like this array in particular, is marked as U property. For a very similar example, another one, get total health. In this particular line, we're getting a crash. So we have in this case it's simpler. M character definition is being garbage collected, and we just need to add U property to it. I wanted to show you this other particular example because of this check that we have here. So actually, we kind of checking like, is this valid before we are accessing it, right? So this is kind of null check from Unreal. It checks if something is null, but it also checks if something is going to be garbage collected. But it doesn't check if something has been already garbage collected. So it won't save you in this case. And it also shows that you need to like understand, especially when you are looking at production crashes, and like the call stack sometimes may be like not pointing you to the place. Maybe something that happened earlier. and it may be because of things like the code has been optimized by compiler, right? So the lines no longer match. So yeah, we just add the property in this particular case. It's a structure in the class. Okay, another one, this time related to lambdas. So basically we have the two events, right? On player profile ready, and we have on player profile login finished. And for these two events, we are subscribing a lambda. And what we found out is that some of these elements that we expected to be there, they've been garbage collected. In particular, this handle that is we were accessing. And the solution at the time it was something like we just we don't use the lambdas in this particular case. We just use regular methods, and this solved the problem. But actually, I was investigating what happened here and why was this happening, and I found two things. One is that Unreal has now a new way to add lambdas into the event. Instead of add lambda, is add weak lambda, and it takes into consideration that something may be garbage collected, and checks before calling something, so you at least don't get a crash. I also found that this bug in particular I was not able to reproduce it in last Unreal Engine version, so it could have been at the time like Unreal Engine bug, where garbage collector was not taking this into consideration properly, because the events are not your properties, and actually you can't mark them as your properties, so the garbage collector needs to consider it like in a different way. Okay, so the final state, we reach a crash-free rate of 98%. We reduce crash per user around 50%, which is a little bit different metric, because some players may have more crashes by average than others. We also reduce app not responding events by 90%, which was great, but not really discussed here right now, very important metric. And what we have left actually to continue working, mostly related to SDKs and Unreal Engine. They have bugs, and that's why you want to keep them up to date if possible. Something that we had trouble with, because we basically when you start modifying the engine, it becomes harder and harder to update. And obviously bugs that were introduced by us in the latest update, which we always need to continue fixing, and that's why it's important that you have such a reporting tool that will tell you that you introduce a new bug. All right, so we go into the last part of the presentation. So this is about RAM optimization. It has to do with the first and the second part, because it's an optimization, and it's solving the problem that if you run out of memory, the game is going to be closed by the operational system. So what did we do? We start by looking in particular to our device with lowest RAM, which is iPhone 6 with 1 GB, and our most memory intensive mode, which is the Kombat. So here we have 6 characters at once. I mean, not on the screen at once, but they are in the memory. We have the arena where they are fighting. We have all the textures, the 3D models, or the VFXs. We have sounds, and we have UI, and of course the game. So if we look at the rundown of one of our worst cases, so this is how it looks like. Most of the memory is used by engine. It is grouping here also our game code and everything. I'm more interested right now in the part above. So these are the meshes, the VFXs, animation, sounds, and textures that we can do something about relatively easily. So basically, in order to do this, you need something like a stat memory. So this is the easiest command you can run on your game to profile what the memory is being used for. So basically, we have texture, how much memory is used for textures or UI textures or character textures and so on. But actually, I prefer other commands like stat LLM, so low-level memory. It shows a bit more interesting grouping of information, so it's divided by engine, textures, animations, and so on. And still, it's not enough in most of the cases. You want something like mem report. So this is creating a huge file. It tells you there everything, all the bytes where they are going, right? Starting from the code, how many instances of the classes you have, textures that you have, sounds, animations, everything is going to be here. So we start looking at what we can trim. So in terms of art and things like 3D models, actually they are already quite optimized. So there is not much we can do there because we taking the models from console version, MK11, let's say, we are making low polys of them. They have around 5 to 10K polygons, maybe 15 for the MK11 characters. And there is quite a modest budget for textures. Obviously, you need to add props to it, like weapons and things like this the characters are using, but we have around 5 to 10 megabytes per character, right? Arenas were also optimized previously. We use static meshes. That's not a RAM optimization, rather CPU optimization, but something to consider. The elements are reused, so if you can, the same item is placed in different places in the scene, but in general, 40 to 60 megabytes. I think it could be optimized more, but it's an artist's job. In terms of VFX, they were one of the first things we work on to optimize because they affect CPU, GPU, memory, everything. So we have a limit on the textures, although some textures may be bigger. We have different LODs for low-end devices. Obviously, the textures, the VFXs are pooled. And I also mentioned here that we use minimal overdraw, so we noticed that in particular, like low-end graphic cards, having transparent textures on top of each other was giving a lot of cost. So we had a tool to spot these cases and rework the VFXs. But in general, we are sitting around 10 megabytes per character in terms of VFXs. Mostly blood. So for the animations, we actually have something that we can work on. So the animations are using a lot of space, and that's kind of expected because we have 4 different skeleton types. So like male, female, guys with 4 arms and so on. And each of them, they have specific bones. So, for example, things like for cloth and for the hair, because we're not physically simulating those at runtime. And we also have a lot of reaction animations. So when one character attacks the other, and they need to perform some synchronized move. It's up to 30 megabytes per character, and these are some of the things we did to optimize it. So basically, we limited the FPS for the animations. 30 FPS is enough in most of the cases. We remove unneeded bones from those animations that they didn't need it because only particular character is going to execute this animation and they don't have those bones. Also, we applied compression, the one from Unreal Engine. So in particular, we're removing every second frame, and that has some problems in some corner cases, some artifacts sometimes, but you can always disable it. And we go down to 5 to 10 megabytes per the character. So this is mostly an artist's job and actually took a lot of time, but they needed us to figure out what was the problem. So we reduced the animations, and this is how it looks right now. The next thing we're looking at is sounds. Sounds are also used in outer space, and what's worse, they were not standardized. They were basically imported as they come from the console version. The newer sounds were very high definition, and to be honest, we we don't need such a definition. A lot of players, they play without the sound or without the headphones. The phone doesn't have such a speakers, right? So the optimizations obviously come from compressing them. Using the Unreal compression, around 40% proved the best, compromise. And we also established the process so they could have separate settings based on the type. So for most of the general sounds, we just have one channel. For the music, we want to have stereo, so 2 channels. And then for some key sounds, we can have like higher sample rate, like skull crashing sounds. And this was actually quite simple and mostly automated. It's a very easy thing to skip because no one knows about sounds. No one knows how to get the best out of them, but actually super easy. And so we almost down to 1 gigabyte. So what can we do next? Let's look at the report we had from before, right? And we can look at textures, right? So here we have all the textures that we using. So 2K texture is using 4 megabytes, a 1K texture is using 1 megabyte. And you can find funny things, like for example, here we have a main menu texture atlas that we are loaded in Kombat. But that probably it's a mistake, right? So let's see what's going on. So we have UI text sprites, right? And those sprites are grouped in atlases. They look something like this. So basically we have, these are for the cards, and we have the frames and some icons, right? And we are always reusing it, or let's say artists always reuse it. So basically, these small icons that we have here, they were part of the menus, and at some point they were used for the Kombat UI. And now suddenly we are loading the whole texture, right? For just these small icons. So some optimizations that you may need to do if you start looking into what's going on with these textures. Basically, you may need to fix memory leaks because basically there is a chance that this texture, maybe you didn't need it at all, right? But it is just there for some reference. You will need to rework the code probably, split atlases, or maybe duplicate information from one atlas to another even. It's better to load only the atlases you need rather than have less atlases, right? So just watch out, atlases can backfire if you don't use them like with a bit of thought on what they're gonna be done for. Okay, so we managed to get under 1 gigabyte for the iPhone 6. This is just a temporary, right? Every time new things are adding to the game, this will go and it will be increasing again. Something that we could do next actually is investigate what's going on with the engine. Why is it using so much memory, right? I did take a look, and actually, like in terms of our game code, right? We don't have a lot of algorithmic calculations that will take memory. We don't have like pathfinding. Our AI is quite simple and it doesn't use memory. So probably something for another talk. And in general, that's everything. So we have, I think, 10 minutes for questions. Just a reminder that you can apply if you want to Sperasoft, and here are some links. Thank you.